Ever thought about crime scenes and, well, how much happens that you just can't see? There's this whole hidden world, isn't there? Microscopic stuff, chemical reactions, telling a huge story.
Absolutely. It's fascinating.
So today, we're diving into exactly that, the core ideas behind forensic chemistry. You asked, and here we are. We've got this great source, Basic Principles of Forensic Chemistry. It covers, well, pretty much everything from atoms right up to lab
It
analysis.
really does. It's quite comprehensive. And our mission today really is to pull out the absolute fundamentals, the key concepts a forensic chemists use day in, day out to
Mhm.
figure out what the evidence is telling them.
Exactly. We want to give you that solid grasp without getting bogged down in like super technical jargon.
Right. Make it clear how they actually do it.
Okay, so the book starts with something really foundational, the scientific method, not just for school, right? It's basically the operating system for forensic work.
That's a good way to put it. The text lays it out. Observe, guess why? That's the hypothesis. Test your guess, see if it hold up.
For,
Reject it or accept it.
and maybe build a theory from there. It's that cycle. The book uses a neat analogy. You leave a room with no windows, step outside, and the ground's wet.
Okay, simple enough.
Your first thought, your hypothesis is probably it rained. Then you look around, maybe see puddles, check for clouds. That's your experiment, testing the hypothesis.
Right. Makes sense. But then there's this other analogy in the book that complicates things a bit. Astronauts landing on different spots on a planet.
Ah, yes. That one's really important for forensics. Imagine one lands in a jungle, another in a desert, on the same planet.
Okay.
Their reports back home are going to sound totally different, describing lush life or barren rock. But both are telling the truth based on their observations.
Huh. So different perspectives, same source, both valid.
Exactly. And that's crucial in forensics. Two different experts might look at the same fiber, maybe, but based on their specific knowledge or the tests they run, they could reach different yet equally supportable conclusions about where it came from. So you really need that unbiased viewpoint, that open mind. It's not always just black and white.
Precisely. The evidence doesn't always shout one single answer. You have to interpret it carefully.
Okay, so scientific method is the guide, but interpretation matters. Let's get down to the basics then, the actual stuff involved. Matter.
Right. The book defines matter simply. It has mass, and it takes up space. Both have to be true.
Mass and space. Got it.
And it makes that key distinction between mass and weight. Weight depends on gravity.
Like on the moon, you weigh less.
Exactly. But your mass, the actual amount of stuff in you, stays the same. So in science, especially chemistry, we talk about mass.
Okay, mass it is.
Yeah.
Then the states of matter, solid, liquid, gas. Pretty familiar.
Yep. Solids hold their shape and volume. Liquids take the shape of the container but keep their volume.
And gases just expand, no fixed shape or volume.
They fill whatever space they're in. And all this matter is built from elements, the fundamental things on the periodic table.
Yeah.
Carbon, oxygen, iron.
The building blocks.
Mm-hmm. And when elements chemically join together, they form compounds like water, HO, 2 hydrogens, 1 oxygen, or carbon dioxide, KO2. Those chemical formulas tell you the recipe.
So how does knowing about HO help a forensic chemist? Where does this basic stuff connect?
It connects through the properties of these substances. The book splits them into 2 types, physical and chemical.
Okay.
Physical properties are things you can measure or see without changing what the substance is. Think color, density, melting point, boiling point.
Stuff you can observe.
Right. Chemical properties, though, describe how a substance reacts, how it changes into something else. Like, does it burn? Does it react with acid?
Ah, okay. Flammability, reactivity.
Exactly. And the book gives a really strong example here connecting the two. Burn patterns in an arson case.
Oh, right. How the way something burns leaves clues.
Precisely. A chemical property, how easily a material burns, creates physical evidence. The depth of the charring on wood, where the fire spread fastest, maybe V patterns on a wall. These physical signs tell the chemist about the chemical reactions that happen.
So like a really deep burn in one spot might mean an accelerant, a flammable liquid, was pooled there.
You got it. It links the fundamental chemistry directly to what the investigator sees at the scene. It's about reading those chemical stories in the physical evidence.
That's really cool. Okay, let's zoom in even more to the atom itself.
The absolute smallest piece of an element that still behaves like that element. The book breaks it down. You've got the nucleus at the center, with positive protons and neutral neutrons.
And electrons orbiting around.
Yep, negatively charged electrons whizzing around that nucleus in specific energy levels or orbitals.
And the number of protons, that's the key identifier, isn't it? The atomic number.
Exactly right. Atomic number equals protons. That number defines the element, 6 protons. It's carbon, always. Mass number is just protons plus neutrons.
Okay, and then isotopes fit in here somewhere. Same element, different number of neutrons.
Perfect. Same proton, so it's the same element, but a different mass because of extra or fewer neutrons. The book notes that adding neutrons can make the nucleus unstable.
Unstable, like radioactive.
Precisely. That instability leads to radioactive decay. And forensic anthropologists actually use this. Radioactive dating, like carbon-14 dating, helps figure out how old, say, ancient bones are.
Wow, another direct application. What about ions? They seem important.
Very. Ions are just atoms, or even groups of atoms, that have gained or lost electrons. So they're no longer neutral. They have an overall positive or negative charge.
Lose electrons, become positive. Gain electrons, become negative.
You got it. Cations are positive, anions are negative. And the book points out it's the valence electrons, the ones in the very outermost shell, that are involved in all this gaining, losing, or sharing. They dictate how an atom reacts chemically.
They're the action electrons, then.
Pretty much. This ties into electron configuration, how electrons are arranged, and something called the octet rule.
Oh.
Basically, atoms want to have a full outer shell, usually 8 electrons, like the stable nodal gases.
So they swap electrons to get stable.
Or share them.
Yeah.
Sodium, for instance, has one valence electron it's happy to lose. Then its next shell in is full. It becomes a positive sodium ion. Oxygen needs 2 electrons to fill its outer shell, so it readily gains them, becoming a negative oxide ion.
So there's the atom as it normally is, the ground state, and then the state it prefers to be in, often as an ion with that full shell.
Exactly. That filled outer shell represents a more stable, lower energy state, which is why these ions form so readily.
Okay, stable atoms achieved. How do they actually connect to form those compounds we talked about, molecules and such?
Right. So first, chemists need a way to count atoms, which are obviously tiny. That's where the mole comes in. It's just a number, a huge number. Avogadro's number at 6.022 times 10 to the 23rd particles.
A chemist's dozen, basically. A really, really big dozen.
Kind of. And the molar mass links this number to weight. It's the mass in grams of 1 mole of something. Lets you weigh out chemicals and know how many atoms or molecules you've got.
Bridges the micro and macro worlds. Okay, so atoms link up.
To form either molecules or ionic compounds. The book clarifies this nicely. Molecules generally involve non-metal atoms sharing electrons. That's covalent bonding. Think water, Keogh sugar.
Sharing electrons, got it.
Ionic compounds usually form between a metal and a non-metal. The metal loses electrons, the non-metal gains them, creating positive and negative ions.
Opposites attract.
Strongly.
Yeah.
They form this repeating crystal lattice structure, held together by that electrostatic attraction. Table salt, sodium chloride, NaCl is the classic example. Because it's a lattice, not discrete units, we technically call NaCl a formula unit, not a molecule. A molecule usually implies covalent bonds.
Ah, okay. That distinction is useful. Covalent molecules, ionic lattices. Now, organic chemistry. Sounds complex. Why is it vital for forensics?
Hugely vital. Organic chemistry is the chemistry of carbon. And most drugs, explosives, plastics, fibers, paints, so much evidence is organic. The book starts with the simplest ones, hydrocarbons, just carbon and hydrogen.
Alkanes, alkanes, alkanes.
Yep. Alkanes have single bonds, alkenes have double, alkanes have triple bonds between carbons. That presence of double or triple bonds is called unsaturation, and it changes the molecule shape and how it reacts.
And then you add other atoms, functional groups.
Exactly. Functional groups are specific arrangements of atoms, like the SOH group in alcohols or the CO group in ketones. These groups give the molecule its characteristic chemical personality, how it behaves.
And this is where it gets wild with drugs, right? The book mentions DMT and its relatives.
Hassan, Lofoten-9.
Yeah, it's a fantastic example. They have the same atoms, same formula, but that iso-H group is stuck on a different position on the core structure. They're positional isomers.
Wow.
And that tiny shift makes them different drugs with different hallucinogenic effects. It shows how critical molecular structure is.
Like changing one Lego brick's position changes the whole model. And designer drugs riff on this completely. They're made by tweaking the structure of known controlled substances, often just slightly modifying or swapping out a functional group. The book gives the classic pseudoephedrine to methamphetamine example. Chemically removing an OH group turns a cold medicine ingredient into a powerful stimulant.
Just snipping off one bit.
Sometimes it's that simple, chemically speaking. The book also mentions GHB with its carboxyl and hydroxyl groups, or esters in some opioids. Knowing these functional groups helps chemists identify completely new, illicitly made substances.
Okay, so this chemistry knowledge is the foundation. How do they apply it in the lab? What's the process for analyzing, say, a seized powder?
Right. The book stresses it as a process.
Hmm?
Chemical knowledge supports the analysis. For suspected drugs, it's usually a three-stage thing. First, just look at it, visual inspection.
What does it look like? Powder, crystal, pill, color, packaging.
Exactly. Get initial clues. Second stage is presumptive testing, often color tests.
Quick chemical tests that change color if certain drug classes are present.
Uh-huh. They react with specific functional groups or structures, like the Marquis test for opiates or amphetamines.
Mm.
They're fast, give you probable cause, but they're not 100% specific. They narrow things down.
Okay, narrows it down. Then the final step, confirmation.
Yes, you need definitive proof. The book talks about microcrystal tests. You dissolve a tiny bit of the sample, add a specific chemical region.
And when crystals form.
Yeah, and under a microscope, the shape, the optical properties of those crystals can be unique to a specific drug, like a tiny crystalline fingerprint. The book does mention there can be some debate about how truly specific these are sometimes.
Interesting. Are there other confirmation methods?
Oh, yes. Before getting to big instruments, sometimes chemical extractions are needed. Think making coffee hot water extracts compounds from the beans, right? That's solid liquid extraction.
Okay.
Chemists use similar ideas, maybe acid-base extraction, to separate the drug from cutting agents or other junk based on its chemical properties, like how it dissolves in acidic versus basic water. pH is key there. Clean up the sample before the big tests.
Which brings us to the fancy machines. Chromatography.
Absolutely. Chromatography is all about separation, separating complex mixtures into individual components. The principle is that different chemicals will stick differently to a surface, the stationary phase, as they're washed over by a solvent or gas, the mobile phase.
Like the sticky marbles analogy the book uses.
Yeah, or think of paper chromatography ink separating into colors on wet paper. TLC, thin layer chromatography, is similar. You can calculate an RF value, how far something travels, and compare it to standards.
But the main one seems to be gas chromatography, GC.
It's a workhorse, definitely, especially for things that can be vaporized, drugs, accelerants, alcohols. The sample is injected, vaporized, and carried by an inert gas through a long, thin column coated with the stationary phase.
And different things come out at different times.
Exactly. Based on boiling point and how much they like interacting with the column coating, the time it takes to come out is the retention time. It's like that coin sorter machine. Different substances take different paths or speeds through the system.
But that time alone isn't always proof, is it?
Generally not considered specific enough on its own, no. Two different things might coincidentally have the same retention time under certain conditions. You need more. You need a definitive ID.
Enter mass spectrometry.
MS. Exactly. MS is the identifier. It takes the molecules coming out of the GC, blasts them with electrons to break them into charged fragments, ions,
Oh, it smashes them up.
in a controlled way. Then it measures the mass of those fragments. Each molecule breaks apart in a characteristic pattern, creating a unique mass spectrum. It's like a molecular fingerprint. You look for the molecular ion, the whole molecule minus an electron, and the pattern of smaller fragrant ions, especially the most abundant one, the base peak.
And GC plus MS, that's the powerhouse combo.
That's the gold standard for a lot of forensic drug and toxicology work, yes. GCMS. The GC separates everything out beautifully, then the MS tells you exactly what each separated thing is. The book gives the example of meth versus phentermine. Tricky on GC alone, maybe, but their mass spectra are totally different. Unambiguous ID.
Makes sense. Separate, then identify. The book also mentions iris spectroscopy.
Infrared, yeah. It's another technique good for identifying functional groups. It measures how molecules absorb infrared light. It doesn't usually give the whole picture like MS, but it's great supporting data. Sometimes it can help distinguish isomers that GCMS might struggle with.
So incredible analytical power. The book really hammers home something else. Documentation. Seems almost mundane, but critical.
Oh, absolutely not negotiable. The mantra is, if it's not written down, it didn't happen. Or, legally speaking, it might as well not have happened. Everything has to be documented meticulously.
Why is it so vital?
Accountability, integrity, reproducibility. Court requires it. You need to show the evidence wasn't tampered with, that the tests were done correctly, and what the results actually were. Memory fails, written records don't.
And the book mentions three main components.
Generally, yeah. First, chain of custody. That's the logbook tracking the evidence. Who had it, when, where, why, from the moment it's collected until it's in court. Prevents any gaps or questions about handling.
Okay, tracks the item itself.
Second, the case notes. That's the analyst's own workbench record. Detailed, written as they do the work. What they observed, what tests they ran, instrument settings, raw data, any problems encountered. The
The
nitty-gritty,
diary of the
pretty
analysis.
much. And finally, the case report. That's the formal summary for the court, the lawyers, the investigators. Describes the evidence, methods, results, and the analyst's conclusions, all clearly laid out. Needs to be understandable, accurate, and complete.
Rigorous science needs rigorous paperwork. It all fits. The book finishes with a quick look at clandestine labs.
Yeah, it's a specialized area. There's not just about identifying the final drug, say, meth. It's about proving manufacturing was happening. So chemists look for precursors, like pseudoephedrine,
The starting material.
and other essential chemicals, like red phosphorus or iodine for certain meth recipes, or even chemical byproducts left over from the reaction. Finding those helps prove someone was actually making the drug, not just possessing it.
So tying all the chemical pieces together to show the whole illegal operation.
Exactly. It connects back to identifying specific elements and compounds using various tests.
Wow, okay, so from atoms and molecules through reactions and properties to these sophisticated machines and crucially writing it all down, it really is a connected process.
It absolutely is. That fundamental chemistry lets analysts decode the evidence, and the careful process and documentation allow them to present those findings reliably, providing that unbiased scientific story.
It really gives you an appreciation for the science behind the scenes in justice. Makes you wonder maybe about where this tech is heading next, doesn't it? Or even the ethics around constantly chasing new designer drugs.
Definitely food for thought. There's always more to learn, whether it's the deep chemistry of a specific drug class or the history of how these techniques developed.
Well, that's our deep dive into the basic principles of forensic chemistry. We really hope that gave you a clearer picture of this really intricate and important field. Thanks for joining us.